All right, welcome to our little expose on graphing functions. So we've taken and we've graphed lines before, we've done that, but now we're going to graph all these other functions and type of equations that we've been working with all year. And we could have gone along with each chapter, when we did absolute values and quadratics and square roots and rationals and exponents and graph them then, but I wanted to graph them all together so that we could see some similarities in and apply some common techniques and threads to all of them. Yes, all of the graphs are going to look a little different, and we'll get to that as we explain things, but I wanted to take a second first and think about, what really happens with each of these graphs. But first we need to know, what are these graphs? So the first thing, and these are the 6 families of functions of graphs, so we're going to look like linear graphs, absolute values, quadratic graphs also known as parabolas, square root graphs, graphs of rational functions, and graphs of exponential functions. So these are the 6 types of functions and the families of graphs we're going to look at. So let's look at building each one by one. So I'm going to kind of talk through the values that we look at in our table for each of these. So for a linear function, y equals x. Y equals x, the basic value of this, the value of our x value is of our y value. So if we look at our coordinate plane and we have our x's and y's, if x is 0, then y is also 0. If x is 1, y is 1. We can fast forward and say if x is 1, 2, 3, 4, 5, y is going to be 1, 2, 3, 4, 5. Likewise, if x is negative 7, 1, 2, 3, 4, 5, 6, 7 in the negative, the y is going to be negative 7. 1, 2, 3, 4, 5, 6, 7. So we've plotted some points. We'll connect the dots through. And that is our base of a linear graph. We've worked with linear graphs way before. All of chapter 4, chapter 3, 4, those were all linear graphs, even some in chapter 5. Now, we dealt with absolute value equations a little bit earlier, but we haven't ever graphed an absolute value. Remember, an absolute value always yields a positive result. It always yields a positive result. So if we have x equals 0, that's also 0 for y. If x equals, let's say, 2, y is also 2. X is 4, y is also 4. But if we said, x is negative 1, well, y is always going to be positive, so y is then 1. If we said x is, say, negative 3, the y is, though, a positive 3. And we have, let's see, 1, 2, 3, 1, 2, 3. And it goes on such that when we connect the dots here, our absolute value graph looks like a V. We have a V-shaped graph for our absolute value. You can't see my arms, but I'm making a V. 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 Absolute value makes a V shape. A quadratic graph is when y equals x squared. So when we plug in some values to see what does this graph look like, if we have x equals 0, 0 squared is also 0. Well, 1 squared is 1. Now here's where it gets fun, because if we plug in 2, x equals 2, 2 squared is going to be 1, 2, 3, 4. All the way up there. 3 squared, 9. So 3 we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Now what would happen when we plug in some negative values? Negative 1 squared, remember that's negative 1 squared, negative 1 times negative 1 is a positive 1. Negative 2 squared, well that's going to be a positive 4. And negative 3 squared is going to be a positive 9, giving us, when we connect the dots, a parabolic or a parabola shaped graph, looking kind of more like a U, not a V like absolute value V, but a U for a parabola. That's going to be our quadratic function. Now a square root function, we need to be careful, and when we plug in, 0, 0 still for the base of our family. Now, the square root of 1 is 1. Great, now here we need to be careful. Square root of 2, we could find some decimal approximation. But let's jump to 4. The square root of 4, that's 2 there. Again, square root of 5 we could guess, but if we jump to the square root of 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, that is 3. Now, let's think about if we plugged in negatives. The square root of negative 1. Right now in Algebra 1, we don't deal with negative square roots, and quite frankly, negative square roots are imaginary, so you wouldn't see a visual representation of them on a graph. So instead, the absolute value graph looks like such. There it is. Now, the last thing to look at, and by last thing I mean two more things, is we have some other graphs which are a little bit tougher to conceptualize. We have a rational function, 1 over x. Now 1 over x, if we think about, if we have 1 over 0, that's undefined, so we can't graph anything at 0. In fact, there's going to be an asymptote. There was an asymptote. We'll talk more about that tomorrow, at 0. Now let's think, if we plug in 1 over 1, well, that's 1. Now if we plug in 2, 1 over 2, that's a half. Well, shoot, we're kind of getting a little skinny over there. Think about this, if we plugged in 1/2, 1 over 1/2, well, that's technically 2, so 1/2 would be 2 right there. Turns out, in the positive side, the graph of this rational expression looks kind of like this, in that it never gets to the axis and just gets as close as it possibly can to the axis without touching. Now, when we go in the negatives, if x is -1, y is -1, that's easy. If x is -2, y is -1/2. So right there, and then we could say -3rd, -4th, etc. If x is -1/2, well then y is going to be -2, and we could keep counting it in that way. So in the negatives, we have this going on down here. So a graph of our rational expressions are going to look like this, more or less, where there's an asymptote where the lines cannot cross, going up and down at x equals 0, also at a horizontal value that we'll talk about later. Now, when we have exponential functions, for right now we're always going to be looking at when the base is 2. Base is 2, so y equals 2 to the x. Well, let's plug in some values. When x equals 0, anything, if you remember, to the 0 power is 1. So this is going to be one of the only two graphs that don't have a 0 point. So in 0, x equals 1. When x equals 0, y equals 1. When x equals 1, 2 to the first power is 2. When x equals 2, 2 to the 2 is 4. When x equals 3, 2 to the 3 is 8. If we could keep going, 2 to the 4 is 16, and we would plot that, like way up here. Now let's go backwards, -1. 2 to the -1, well, that's 1/2. 2 to the -2, that's -1/4, which we would sneak like right in there. So when we connect the dots, we have this as our exponential function. And again, we get close but never touch, because there's no way that if anything goes to an exponent that it'll be 0, so we never quite fully touch that value. Now, so we have our general 6 families of graphs. Here they are. Woo. Let's talk about transforming these graphs. Because do all lines look like this? No. Are all absolute value graphs going to look like this? No. There's ways that we transform these graphs. Now for lines, we know already with lines that we have a general form of y equals mx plus b, where m is going to be the slope of the line that changes, and b is going to be the y-intercept that changes. The y-intercept. So, using some colors here, if we graph, let's say, y equals 2x, so we change the slope to y equals 2x, well, on this same sheet of paper, so that we can compare it to y equals 2x, with the slope of 2, if x is 0, that's still 0. But if x is 1, it turns out now that y is 2. If x is 2, it turns out y is 4. If x is 3, it turns out y is 6, etc., etc. we connect our dots, and we have this line that forms here by changing the slope. Now, if we add a y-intercept, let's say x plus 3, we take that same y equals x graph and we just shift it up a total of 3. So if we look 1, 2, 3, that's going to be our new y-intercept. We still have a slope of 1, and we can connect the dots. And we have our line through there, connecting the dots. Now, we can be fancy and do both. If we do both, I'm going to use purple here. And if we said y equals 2x plus 3, so we change the slope and we change the y-intercept. If I go up to 3 and now have a slope of 2, I have this brand new line. It's still a line. It's still related to that y equals x. We've just transformed it. We've moved it. We've adjusted its slope. We can do that with all of these other graphs, and they take on some general forms that have variables that are very similar. So if we took the absolute value, and it's going to go into this general form of y equals a times the absolute value x minus b plus c. Now, this a value is going to change the stretch. Actually, I'm going to write these up here. A is going to be how it stretches. If we, maybe move it in and out like this, or kind of expand it up and down maybe, that's going to be our stretch. Our b, what our b represents is our horizontal shift. A horizontal shift, moving it left and right. Now, if we have minus b, that's going to be moving it to the right in the positive. If we had plus b, or if it ended up with plus, like plus 2, that would move it in the negative. So with the horizontal shift, we have to be careful to think plus, we're going to go in the negative direction, minus in the positive direction. And this c is going to be our vertical shift. This vertical shift, moving it up and down. So I'm going to show you a couple, 1 or 2 different things of if we changed it per graph. So yes, this video is a little bit longer, but it has a lot that we're going to dive into in class on Monday. So if we took our absolute value and we said maybe y equals 3 times the absolute value of x, well, we would take our absolute value graph here and we would multiply it by 3, thus kind of squishing it by 3. So if we still have this, and we say x equals 0, y is going to be 0. But let's say x equals 1. Well, now y is going to be 3. Let's say, if x was negative 2, well, the absolute value of negative 2 is 2, times 3 is 6, so negative 2, 6 is right there. Oh, yep, 6 is right there. Then, when we connect the dots, we see that this absolute value graph has kind of squished itself a little bit. Now, something that we could also look at is, what if that a was negative? So what if we had, and I'm going to use pink, y, just kidding, I'm not going to use pink, I'll use green. If we had that y equals negative the absolute value of x, negative absolute value of x, well, that negative sign is going to flip our v upside down. So if y equals negative x, 0 is still 0. But if x is 1, let's say, the absolute value of 1 is 1, but negative 1, we're going to go down. And negative 2 would be down there. Now if we plugged in negative 1, the absolute value of negative 1 is still positive 1. Turn negative. And we will compare it and move it down as such. So if we have a negative, that's going to shift it and flip it the opposite direction. So a parabola would open down, a square root would turn under, A rational equation would, if it looked like this, would flip the sides that it's at, and a exponential function would flip down, just like that. All right, so now let's look at some vertical shifts. And vertical shifts, in our quad, I'm going to still use the absolute. Actually, I'm going to shift to the quadratic, and we're going to talk about a different function with our, horizontal shifts. So quadratic, if we wrote it in the form y equals a times the group x minus b squared plus c, this is how we can now identify our, stretching it and squishing it or expanding it, taking it, moving it left or right, and moving it up and down with a vertical shift that we'll see right now. So if I took, and let's say we wanted to do y equals x minus 2 quantity squared, well, that horizontal shift is I'm going to take every point in this x squared and move it to the right 2. So I'm going to move this vertex here. This point moves 2 to the right. This point moves 2 to the right. This point moves 2 to the right, 2 to the right. And my new function lives like this, right there. Now, if that was plus 2, I would have moved in the negative direction. Let's look at if we had y equals now x squared minus 3. Notice that this minus 3 happens outside the square, so that's going to be a vertical shift up and down, a vertical shift up and down. So when we take a look at that, I take from my original family graph, and I move down 3. Down 3. Each of my points then moves down 3. 1, 2, 3, down 3. 1, 2, 3, down 3. 1, 2, 3, down 3. And I have, we can even move this one, 1, 2, 3, down 3. 1, 2, 3, down 3. And I have that same kind of looking graph just shifted down 3. Sorry for my bad drawing there. Now, sometimes, and I'll show you with this square root, we can combine a lot of them into the same. Again, our expanded form of the square root is going to be y equals a times the square root of x minus b plus c outside. So let's say I wanted to, we'll just do a horizontal and vertical shift for right now. Let's say that I wanted, you know what, no, we'll go crazy. We'll go all three. I'm going to explain all this in class when we see each other next. We'll go crazy. Let's say that we wanted to say y equals 2 times the square root of x, let's say plus 3 minus 4. So with a being a stretch, we're going to expand it 2. We're going to move it 3 to the right, and we're going to move it negative 4 down. Sorry, I lied. This is 3 to the left. This is down 4. And we're going to expand 2. So what I'm going to do is, again, kind of if I plug it in, I start at 0, 0. But notice I'm moving it to the left 3, 1, 2, 3, and down 4, 1, 2, 3, 4. So my starting point is going to be there. My starting point is going to be way down here for my square root function right there. Now, instead of, if I were to think that this is my new thing and I go up 1 over 1, I've doubled it. So I would go up 1 over 2. Now notice here, from here to there, I went up 1 and over 3. I'm going to go now up 2 and over 3. So up 2 over 3. Here I went up 1 over 5. I'm going to go up 2 over 5. And here is my new group, my new graph, having done both an expansion, a horizontal shift to the left 3, and a vertical shift down 4. Now, this is all a lot. I know this is a lot of information, that we just went through really quick. You're in luck because for the most part we're not going to do too much with too many shifts of these graphs, but we in the way that this is, but we will do some other things. So their expansion, rational, we have y equals a over x minus b plus c, and we'll plug things in and manipulate it. Exponential will have y equals a times 2x minus b plus c. And we'll play around with these more in class, I promise. For right now, I just wanted to give you a little expose on graphing functions and manipulating them and moving them up, down, and around. And we will play with this a lot more in class tomorrow, I promise.